In this grand cosmic theater, there are four fundamental actors known as the forces of the universe. Yet, unlike the others, gravitation plays a unique role. It's the only performer that doesn't bow out on the large cosmic stage, attracting objects with positive mass and energy, always and without exception. But have you ever pondered why there's only this one-way attraction? Why spacetime bends in just one direction, pulling objects closer instead of pushing them away? Why we don't see, for instance, a cosmic bowling ball lifting the fabric of spacetime upwards and driving away smaller bodies? Well, the answer to why there's no anti-gravity in the universe is, it's a curiosity you'll have to wait for. What's up, my amazing and curious folks? Ready to unravel the mysteries of the cosmos together? I'm your host Caesar, and accompanying me in this interstellar adventure is our star commentator, Sonia Guimaraes.
Hiya, universe explorers. Buckle up, because today's journey is going to be a wild one.
Before we blast off, remember to subscribe to our channel and hit the bell icon to make sure you never miss a moment of our galactic explorations. Welcome to Curiosity Wonderland, where the only limit is the edge of the universe itself. So here's the thing, folks. Our universe, as expansive and enigmatic as it is governed by four fundamental forces. Now, the strong nuclear force, the weak nuclear force, and the electromagnetic force, they all have their roles. They're like the backstage crew of a theater production, working hard to keep everything running smoothly. They ensure protons and neutrons stick together, govern radioactive decays, and even drive the formation of neutral atoms. But when it comes to the grand cosmic stage, these forces step back. You see, they balance out at large distances, rendering themselves as neutral. It's like, when you have a bunch of actors on stage, they all have their parts, but they balance each other out to create a coherent production. Can you picture it?
Absolutely, it's a wonderful analogy.
Great! Now, among these forces, gravitation is the star performer. It's the leading actor that never bows out. It's unique because it only recognizes positive charges, entities with positive mass and/or energy. But here's where the plot thickens. Our friend Alex Jabethner posed an intriguing question. You know the classic analogy used to explain spacetime, the bowling ball on a bedsheet? The weight of the ball deforms the sheet, pulling in smaller objects nearby. But Alex wonders, and rightly so, why can't the bedsheet be deformed in the other direction, pushing objects away?
Like an anti-gravity effect?
Exactly. But here's the catch. We don't observe this happening. Spacetime only bends in one direction, that of gravity. And why is it so? That's where our exploration leads us. Are you ready to delve deeper into the mysteries of our universe? Alright, folks, let's dive deeper. Picture this: the more mass and energy you gather in one place, the more space is curved by the presence of that mass and energy. It's like squeezing more actors onto our cosmic stage. Their collective presence distorts the stage itself, influencing the movement of all characters, whether they are the star performers or the supporting cast. Now, some might argue that this analogy oversimplifies the complexity of the universe. It depicts space as two-dimensional rather than three, and shows the curvature of space as being solely due to gravitation. It may even lead you to believe that far away from a large mass, space isn't curved at all. But take heart, dear listeners, because these objections can be addressed. Imagine space as a three-dimensional grid. But this grid isn't the regular Cartesian one we're used to, where all lines are perpendicular. Instead, it's a grid where lines get drawn inward by the presence of masses. Think of it as someone pulling strings from a Cartesian grid towards a single point. Are you following along?
Yes, it's like visualizing how water swirls around a drain, in all three dimensions.
Spot on. So, when a mass moves through this grid, it's not just distorting a two-dimensional fabric. It's curving all of three-dimensional space itself. This distortion makes for some fascinating phenomena. For instance, multiple masses orbiting each other can cause the emission of gravitational waves. And light passing through this curved space will bend and possibly magnify due to the effects of the curved space. But here's the kicker: it seems that gravity can't work in a repulsive manner. It's as though space can only curve in one direction, the one that attracts, not repels. Back to our bedsheet analogy, matter and energy only ever cause space to curve down, not up, resulting in attraction but not repulsion. And with our three-dimensional grid, the lines are drawn inward, not outward, again, only causing attraction. Fascinating, isn't it? And this brings us to our burning question: why is there no anti-gravity? Why does spacetime only bend in one direction? Let's continue to unravel this mystery together. Buckle up, folks, as we delve into the heart of what makes gravitation not only remarkable, but also utterly unique among the four fundamental forces. There's only one sign for gravitational charge in the universe, and guess what? It's positive. This isn't typically how we talk about gravitation. We often focus on mass and energy, but, interestingly, we've never discovered such a thing as negative mass or negative energy. In fact, overall, mass and energy must always be positive.
So, in a way, gravity only understands positivity?
That's one way to put it, yes. Now, compare this to a force like electromagnetism, and you'll begin to see the stark difference. Electromagnetism recognizes two types of charges, positive and negative. It functions according to certain rules. Positive charges repel each other, as do negative charges. But a positive and a negative charge? They attract each other. The direction the net force points depends on whether the charges are alike, which leads to repulsion, or opposite, which leads to attraction. Now, here's an interesting tidbit: the electromagnetic force is much stronger than the gravitational force. Imagine putting two positively charged protons close together. The repulsive electric force would dwarf the attractive gravitational force by a factor of about 1 followed by 36 zeros.
Well, that's a huge difference. So, why doesn't the electric force dominate the universe instead of gravity?
That's the question we'll be tackling next. Let's continue our exploration. This is getting more and more fascinating, isn't it?
This conversation takes me back to my childhood, to a time when I was fascinated with magnets. I remember playing with a pair of them, watching in amazement as they either repelled or attracted each other, depending on which way I turned them. The invisible force was so magical to me, a mystery that propelled my curiosity into the world of science.
That's a lovely memory. It's almost a metaphor for what we're discussing, isn't it?
In a way, yes. My youthful fascination mirrors our current exploration of electromagnetic and gravitational forces. Just like my magnets, positive and negative electric charges balance each other out in the universe. Atoms are electrically neutral, with the positive electric charge of the nucleus exactly matched by the negative electric charge of the orbiting electrons. Even stars and galaxies, made predominantly of atoms, are electrically neutral overall.
And yet, despite being so much weaker than the electromagnetic force, gravity seems to rule the roost on a cosmological scale.
Exactly. This happens because gravity is cumulative. It's like the shy kid in class who doesn't say much, but when they do, every word counts. There's only one type of gravitational charge, and it adds up over time. It's not the flashiest force, but on extremely large cosmic scales, gravity is arguably the only important force.
That's an interesting way to put it. And what about the other two forces, the nuclear ones?
The weak and strong nuclear forces. They're prohibited from influencing large scales due to their own unique properties. But let's delve into that a bit later. For now, let's allow our listeners to sit with the image of the quiet yet cumulative gravitational force shaping our universe.
Now, let's discuss the strong nuclear force. Interestingly, it's mediated by gluons, which are massless, just like photons that mediate the electromagnetic force. But here's a fascinating twist: the strong nuclear force has not one, not two, but three types of charges that are all interconnected.
Hold on, 3 types of charges? That sounds like a new level of complexity.
Indeed, it is. We often use a color analogy to explain the strong force. We talk about red, green, and blue as the 3 colors, and cyan, magenta, and yellow as the 3 anticolors. The combination of a color and its anticolor is colorless, and so is the combination of all 3 colors or all 3 anticolors.
So, in essence, it's like an artist's palette, but for nuclear physics?
You could say that. Only quarks and gluons have color among the fundamental particles, and they can only exist in colorless states. These include baryons, antibaryons, mesons, and other more complex, shorter-lived states.
So that's why it's short-range like the weak nuclear force?
Precisely, because all mesons are massive, this residual strong force, as it's known, is also short-range. So on cosmic scales, that really just leaves us with gravity. All masses and energies are positive, so the gravitational force must always be attractive. But imagine a different universe, one where negative mass or energy states could exist. Gravity is unique. It doesn't function like the electromagnetic force where opposite charges attract and like charges repel. If we lived in a universe with negative mass or energy states, things would be different.
Different how?
In such a universe, positive mass or energy states would attract other positive states, but they'd repel negative states. Similarly, negative states would attract other negative states, as well as positive ones.
So in this alternate universe, we could shield ourselves from gravity?
Exactly. If negative mass or energy states were real, we could manipulate them to shield ourselves from the gravitational force. We could experience weightlessness without needing to be in freefall.
And what about the possibility of creating spacecraft with artificial gravity?
With sufficient amounts of positive and negative energy states, we could set up spacecraft floors with positive energy states and ceilings of negative energy states. This would create a uniform field of artificial gravity, much like the uniform electric field inside an electromagnetic capacitor.
Does this tie in with the big idea behind the occupier drive?
Yes, indeed. The occupier drive concept relies on the existence of negative mass or energy states to create a warp field. This would allow the space in front of a spacecraft to contract, the space behind to expand, and keep the space where the craft is located flat, preventing damage from gravitational tidal forces. However, one crucial component of this theory, the idea that antimatter would behave as if it had negative gravitational mass, has been disproven. So, our best hope for a realistic warp drive is pretty much dashed, unless we discover new physics.
So, for now, it's just a fascinating theoretical concept. But who knows what future discoveries might unveil?
Is it possible to observe or test the effects of gravitational repulsion without invoking new physics? Can we create a setting in which the gravitational force can be negative instead of positive? Interestingly, it's not entirely impossible.
Oh? How so?
Let's imagine a scenario where space is uniformly filled with matter, like a perfect fluid. Within this fluid, we can introduce two types of particles, a positive mass particle with a density greater than that of the fluid and an effective negative mass particle with a density lower than that of the fluid.
So we're essentially talking about something denser than the fluid and something less dense?
Precisely. In this setup, both positive mass particles and negative mass particles would attract each other. However, a positive mass particle and a negative mass particle would repel each other.
So, there's a sort of gravitational repulsion happening here?
In a relative sense, yes. A lower density region within a uniform mass fluid behaves as if it has negative mass or energy and experiences gravitational repulsion. However, on a fundamental level, there are no negative mass or energy states. Even empty space has a small, yet positive amount of energy, as determined by measuring the effects of dark energy.
So while we can manipulate space to create lower energy regions, these regions still experience an attractive gravitational force.
That's right. Even though we can potentially create an effectively negative energy region compared to the average mass or energy state, the gravitational force within that region remains attractive. So, in the end, it's all relative. Now, it's important to understand that a less attractive region of space is not the same as a region with negative gravity. Consider a helium balloon floating in a car. If you slam on the brakes, everyone lurches forward, but the balloon floats to the back.
So, it's not that the balloon is violating the law of motion, but that the dense air in the car is remaining in motion more strongly than the lighter helium in the balloon.
Exactly. And that's the only sense in which we have anti-gravity, if you will, where something with less mass or energy behaves like a negative source of gravity, but only in comparison to something with more mass or energy.
So until we discover new physics that allow for the existence of negative mass or energy states, anti-gravity will just remain a mathematical curiosity?
As it stands now, that's correct, but science is always evolving. Who knows what we may discover in the future? For now, the concept of anti-gravity remains an intriguing topic of discussion and speculation. So, folks, there we have it. We dived deep into the intriguing question of why there is no anti-gravity in the universe. We explored the unique nature of gravitation, the balance of forces on large scales, and the absence of negative mass or energy states. It's safe to say that gravity really does keep us grounded, and in more ways than one.
And if you've ever wondered why you're not floating off into space right now, well, now you know. It's all down to the fascinating science of gravitation, the irresistible force that keeps us all rooted.
And remember, there's always something new to uncover in this vast universe. So, until we fly off to our next curiosity, stay curious and grounded.
Absolutely. And if you enjoyed this episode, don't forget to blast the like button, leave a comment, and share the episode with your friends. Knowledge is best when shared, after all.
Wishing you all a gravity-filled day.
Goodbye, and keep wondering.
Our exploration today was based on the insightful article, Ask Ethan, Why Is There No Anti-Gravity?, authored by Ethan Siegel, published on Big Think on December 1, 2023. If you're curious to dive deeper, you can find the full URL in the video description. Alright, now I'm off.